Hello and welcome to another chemistry video. This one's about arenes, and when you go into second year A-level chemistry, it's probably a word that you've never heard before. In fact, there's lots of words that you haven't heard before that you find in chemistry. But anyway, arenes, all you need to know about that word is it means compounds containing benzene, which we'll talk about in depth, also called aromatic compounds. But arenes is fine. You know what it means, and there's an alternative name for them. So this was discovered quite some time ago. It was just a molecular formula, and the scientists at the time had to come up with a structure for it. And the thing that strikes you most about it, or strikes me most about it, is how few hydrogens it's got. So how are we going to draw a structure that has that formula and all the atoms in the molecule are actually sufficiently bonded to satisfy their valence requirements? That was a bit long-winded. So if you look at hexane, obviously that's not it, because that's C6H14. And that's just a straight chain. So we'll draw the skeletal formula. 1, 2, 3, 4, 5, 6. Now, if you join the ends together, you can lose 2 hydrogens because you don't need as many. Because if you've only got 2 hydrogens on there, and that's the same on all of the carbon atoms, that carbon atom there has got 4 bonds to it, so that's all fine. If you want to lose another 2 hydrogens, you could put a double bond in, but we're still not down to C6H6, so we need to lose another 4. So how about we put in another 2 double bonds? So we've actually got, in theory, we now got 3 double bonds. So that's an idea of what benzene could have been. And somebody called Kekulé actually came up with this structure. Apparently he had a dream. It turned out to be a nightmare because he wasn't right. He imagined that this was a snake and it was biting its tail. And then for some reason, and then he put these double bonds in, which is fine. That gives you C6H6. Is it benzene? Not really. It was when I did A-level, we were satisfied with that. But nowadays we draw benzene like this. And I'm going to explain why. So in that one, there are actually no double bonds. I think you can see that there's only 1 hydrogen on each one of these. There can only be 1. And this one is properly the structure of benzene. There's 1 hydrogen on each one of these. Now this one would be called, let's see, cyclohexa 135 triene. I don't think you need to remember that. You could probably work it out for yourself. So that's a theoretical molecule, because I'm going to show now how it doesn't exist. Cyclohexa 135 triene. It isn't like that, and we can very quickly explain why that is. So let's clear things up a little bit, or a lot. So let's look at what's wrong with this. Nice idea. Solves the problem in principle. Meets it. The only good thing about it really is that it actually does agree with the molecular formula. That's it, because there's problems there's problems with this. The first one is, if it was like that, double bond, single bond, double bond, single bond, double bond, single bond, you would expect it to have two bond lengths. In other words, these stronger bonds would be shorter and the single bonds would be longer. So the first problem is, it can't be like that because all bond lengths are the same. And I mean CC bond lengths. So that's a bit of a blow to Kekule's theory already. And when he woke up after his dream, if he put some bromine water in, he might have got a bit of a surprise. And he might have thought again about who he was going to tell about this, because if you add bromine water to that, you would expect it to react, wouldn't you? You've seen at AS the reactions of double bonds with electrophiles, electron pair acceptors. Well, it doesn't react with bromine water. So there's no reaction when you put Br2 in it. So it won't decolorize bromine water, which is a big red flag saying it can't be anything like that. And the third one is, you've got 3 double bonds. Now, if you think about cyclohexene, if we add hydrogen to it, we would get, well, we would break the double bond. There's no other products. That would be electrophilic addition. Well, it doesn't do that either. Now, the delta H for that will be important in a minute. So we reckon, or I don't reckon, Kekule reckoned that it was this, which we're going to finally put an end to that idea. So this time we're going to need 3 H2s because we're breaking 3 double bonds, not just one. And we end up with the same result. And there's another delta H, I'll call that delta H1, and this delta H2. So in theory, delta H2 should be about equal to 3 times delta H1. Well, it isn't. It's nowhere near 3 times. It's more, but it's not 3 times. That's H1. That's H2. This should be 3 times bigger than that because there's 3 double bonds instead of 1. It just isn't. And that explains why we draw benzene like this these days. It's not the easiest thing to draw. Always make sure you do a decent sized benzene ring because you may have to do mechanisms with it. Now what this means is, this ring here, the inner ring, it means the electrons there are some delocalized electrons in p orbitals. And p orbitals, don't usually talk about this much in A-level chemistry, but they're shaped like a dumbbell. We won't go into too much detail. Now the benzene ring itself is planar. In other words, flat. So these carbon atoms are all flat. They're all in the plane of the screen, if you imagine it like that. The p orbitals poke up and down, and they all overlap to some degree, above and below the ring, all around the ring. So the electrons are not centered in any particular place. These are p electrons. Just so happens that's the shells, the subshells that they're in. P electrons are delocalized. Don't worry too much about the detail of that. So electrons are equally spread out most of the time. If you take a probability, they could be anywhere, but let's not go down that road. The electrons are evenly distributed. We'll say that for the purposes of A-level. On average, evenly distributed. Now, the other thing is, this has got a very high electron density because these p electrons can't get delocalized because there's no other p orbitals for them to, with bonds in, for them to overlap with. So they just stay around there. So you've got a very high electron density, and that will react with that. You'll have trouble getting this to react with that, but you can do it. So the electrons are spread out. So this does not go electrophilic addition. So benzene, no electrophilic addition. So that means that rules out a lot of reactions that we would expect when you've got a double bond. So there's all the evidence, most of it anyway, that proves that experimentally this is just not going to happen. Everything you look at contradicts this structure. So there are no double bonds. The electrons that would have been in the double bonds are distributed above and below the plane of the ring. That's all you need to know. So they're a bit diluted because of lower electron density. Now there's all sorts of arenes, and that's just the most basic one is benzene. So now you know a little bit about the structure of that and why we can't go along with this, even though right through my A-level all those years ago, we always used this structure and it worked. It really did work for the mechanisms, but it doesn't exist, so it's wrong. If some other evidence comes up to dispute this, then of course the scientists will look at it, but it's very unlikely. I mean, look at all the evidence there. Simple, straightforward evidence. It just doesn't exist like that. So that's the end of the video. The next video that I shall make will be about some of the reactions of benzene. Now that we know the structure of it, we can look at some of the reactions of it. So thanks very much for watching. If you found it useful, please click the like button, and I'll be very grateful for that. So I will see you in the next video, I hope.